SwayamPrabha. Digital India. Educated India.
This is the last lecture of our course, and in this we would begin by discussing about one of the so-called other applications of shock waves by looking at one or two simulations related to astrophysical flow applications. And then we would have a quick recapitulation of the main topics covered in this NPTEL course before we complete. As far as the astrophysical flows are concerned, as you can see here, we have the first example as a high Mach number under expanded jet. So, to begin with that, we look at the 2D compressible Euler equations. That means we are essentially talking about an inviscid high Mach number under expanded jet. This of course must be now very much familiar to you. It is a continuity equation. It is in index notation, so you can understand that there will be a number of terms coming out of the repeating index. Then comes the momentum equations, the time dependent term, the advection terms which makes the material derivative, and then comes the stress terms on the right hand side. And as you can see that the sigma ij term does not account for the viscous terms. As far as mu b is concerned, it is the bulk viscosity. For these class of simulations we have taken it to be 0, and the other term of course is the pressure gradient term with the Kronecker delta associated in both the expressions. Then comes the energy equation, and that essentially completes the system of conservation equations, but you need also additional equations to close the system. We have discussed this on numerous occasions earlier, so I hope by now you are comfortable with that. So, having said that, we look at a few more details about the numerical methodology, the kind of boundary conditions we apply, the domain dimensions, grid size, etc. So, this is essentially the kind of domain we are talking about. It is like a rectangular domain, where along the x direction we have 40 units length. Everything is non-dimensionalized here. Along the y direction we have 160 units, and the width of the jet which emanates from the bottom part of the domain is unity. So, the jet width you can consider it to be spanning from 0 to 1. So, that is basically the region that we are talking about, y equal to 0 and x less than equal to 1. That is basically the inlet from which the jet is emanating. All the remaining boundaries on the right and top and portion of the bottom are considered to be outlets, where wave transmissive kind of boundary condition is applied, while at x equal to 0 this boundary is considered to be a symmetry boundary. If you look at the grid points, a very large number of grid points have been deployed, which makes it about 50 million or 5 crore grid points. So, this needs a lot of computing effort really, and you need to have a high performance computing system like the ones we were discussing a few lectures back. And as far as the numerical methodology is concerned, of course, we are solving two dimensional Euler equations. So, it is a two dimensional Euler solver. Time integration scheme is third order Runge-Kutta method. The inviscid flux calculation is done with the AU SM plus scheme with fifth order Winnow scheme for flux reconstruction. So, these are advanced numerical methods which are used for appropriate calculation of compressible flows laden with strong shocks, and you need to put in some more effort to understand the computational issues related to such schemes. Under the ambit of the present NPTEL course, of course, we cannot go too much into details of that because there is no time for doing that, but you can of course explore on your own, which you are encouraged to. We also use flux limiters for clipping oscillations about shocks, and that is done through Van Leer flux limiter. So, this is some detail about the simulations, and now you see kind of image which represents the kind of flow field you can expect around such a high Mach number under expanded jet. Here the jet that is emanating out from here is considered that of argon. It is a argon jet expanding into air. It is kind of modeling stellar wind like the way we see in astrophysical flows, and it is the view of the under expanded jet at non-dimensional time of 500 units. So, the T star that you see over here is actually representing some kind of a non-dimensional time, not to be mistaken as seconds. And then if you look at the pressure ratios, density ratios of the pressure and density at the inlet in connection with the stagnation values, the corresponding stagnation values, you see very large ratios. That means that stagnation pressure ratios are extremely, the stagnation pressure as well as density ratios are extremely high. So, here we are talking about 2000, while in terms of density it is as high as 20,000. So, these are extremely large values which we generally do not talk about in the kind of aerospace applications we have seen earlier, and typically this is a range which fits astrophysical flows. The static temperature at the jet exit is about 150 Kelvin. In these simulations we have neglected many effects. For example, at so low temperatures, as the flow expands further, there will be further drop, and then liquefaction of the media can happen, but such effects have been neglected. If you look at some broad features of the flow field, you can, if you zoom deeply, though here in this view it is not so very evident, expansion waves are formed near the jet exit because of the under expansion. Kelvin-Helmholtz instabilities are formed in the shear layer because of the very high velocity differences between the jet core and the quiescent neighborhood, and then this supersonic flow would terminate in the form of a Mach disk, and then you see very widely varying structure shapes, where large scale structures may be visible in a region like this, while in regions like this, if you zoom deep, you will find very, very small structures. So, there is a wide range of scales in terms of both space and time. So, this is the kind of simulation which could be a kind of simplified modeling of stellar wind. We put up another example, that of an accretion disk, where we have a kind of a singularity here at the center, and then if you look at a region like this, notice that the brighter bands are corresponding to very large densities, and the darker bands are lower densities. A blob of fluid mass introduced into the domain is imparted with some forced vortex motion in that region that you see over there. Additionally, it is also perturbed with time, with forcing appropriate to sustain a longer stable movement of this mass within the accretion disk. So, as it moves through the accretion disk, the mass gets stretched as it moves, and it creates density waves. So, you can see the kind of an elongating effect that is happening over time. Shock waves are formed within the so called spaghettified layers formed within the accretion disk. So, as the mass gets stretched, as it moves through the accretion disks, we say that layers of spaghetti like features are formed, and within those layers we do not only see density waves, we also see shock waves embedded. So, this is a typical, again somewhat simplified modeling of an accretion disk. Number of effects have not been modeled, but again broadly some of the major effects are visible in this simulation. So, these are some applications which cater to astrophysical kind of flows, and two important references which you might look at in your spare time, which might help you to explore further in this direction, have been put here. So, the first paper, Bodo, talks about stability and nonlinear adjustments of vortices in Keplerian flows. You remember that word Keplerian was mentioned in the previous slide too at the bottom. So, if you read through this paper, probably you will get better idea of what we are talking about. The second paper, that of Mignon et al., again in the same year, related to a numerical code for computational astrophysics. So, these are papers which might be very useful. We come right to the end or the last portion of the course, where we try to look back briefly, try to recapitulate what we have tried covering in this course. Right from week 1, if you see that we started from the basics, we talked about definitions of supersonic and hypersonic flows. We introduced basic concepts like compressibility, compressible flow, definition of Mach number, and then transition of a flow from subsonic to supersonic to hypersonic conditions. We discussed about the basics of laws of thermodynamics, equation of state. We also looked at different governing equations of the flow field, starting from the more fundamental velocity potential equation, for example, and then trying to build up more complex governing equations which can model more effects. All the way we have also taken note of the different assumptions which are embedded into each modeling framework. Flow through CD nozzle and a supersonic wind tunnel, flow over thin lifting surface over a range of Mach numbers, brief discussion of characteristics of hypersonic flow are some of the things we then took up. We also in between talked about optical flow visualization techniques, which may give us better understanding of the flow when we try to see them, so to say, using some optical methods in supersonic or hypersonic wind tunnels. Shock tubes and hypersonic wind tunnels, normal shock, oblique shock, Prandtl-Meyer expansion fan. So, these are important topics which we further discussed briefly, because that was an initial week. So, we tried to take an overview of some of the important things we were about to learn, and we also mentioned about some so called other applications, including lithotripsy or cosmic shocks. Of course, we discussed them right at the end of the course. In fact, during the last 2 lectures we have been discussing about them more elaborately, and that is how we tried to wrap up a lot of material under this course, which addresses most of the supersonic as well as hypersonic flow applications broadly. Looking deeper into different tools to analyze the flow field, we looked at Lagrangian and Eulerian approach, control volume and differential element approach, and then we later showed that the different conservation equations can be represented in terms of these different approaches of looking at the flow field. The governing equations of compressible flow were introduced, along with some very basic concepts like fluid element trajectories, streamlines. We also learned about the index notation, which is so very important for compressing or compacting the system of equations and representing them in a very simplified manner. We introduced or rather revised quite a bit of mathematical tools here, where we looked at gradient of a scalar, divergence of a vector field, line, surface and volume integrals, compressible continuity momentum energy equations, Navier-Stokes equations. So, a lot of material which you all have perhaps learnt in other courses of fluid dynamics were recapitulated here, reintroduced, revisited for convenience and revision. Then we discussed at length, and several times we have actually revised the concept of thermodynamic pressure and mechanical pressure, basic concepts, fundamentals like angular velocity, vorticity, rotational flows, stress and strain rate, irrotational flow and the presence of a velocity potential, and all these concepts helped us to further analyze the conservation equations from a fundamental angle in a more confident way. We looked at small perturbation form of velocity potential equation, and then we looked at the hypersonic small perturbation equations, and this is a place where we probably realized that hypersonic small perturbation equations are a bit different from their supersonic counterpart. We introduced the Newtonian theory of hypersonic flow, and we tried to look at how the flow behaves past a thin lifting surface like a flat plate when we look at it from the Newtonian theory. In the next week, we looked at waves, because waves very widely appear in compressible flows, and we understood that mathematically such behavior is classified as hyperbolic partial differential equation. We looked at linear waves in the form of acoustic waves, finite or nonlinear waves, which are stronger waves which do not anymore have the linear behavior, and very strong compression waves form the shock waves. Then we looked at the theories encompassing normal shock and oblique shock, the governing partial differential equations, how they simplify across say a one-dimensional normal shock. Oblique shock, of course, always by definition is two-dimensional, at least if not three-dimensional. And then we saw how continuity, momentum, energy equations are applied across such fronts. We understood what is characteristic Mach number. We looked at Mach waves, and then we started applying the shock and expansion wave relations in the high Mach number limit, with the intention that we were trying to extend them to the hypersonic limit, which essentially is a higher supersonic Mach number range. We looked at hypersonic similarity parameter, and then we tried to look at the Newtonian theory once again, trying to solve some problems and so on. Then we revisited the waves, the theory and numerical solutions, governing conservation equation for viscous and inviscid compressible flow, and so on, before we wrapped up this week. In week 4, we started discussing about viscous dissipation and consequent heating of the flow, that basically referred to the compressible Navier-Stokes equations. We looked at the similarity parameters which govern such flows, and we saw that ratio of specific heats, Reynolds number, Mach number, Prandtl number, these are the parameters which are of paramount importance when we deal with compressible Navier-Stokes equations. We did an order of magnitude analysis of the compressible boundary layer equations, and we got their reduced form, and we correspondingly looked at hypersonic boundary layer equations, and we could see the differences. We discussed about self-similar and non-similar solutions of boundary layer equations. We also recapitulated the Blasius solution for incompressible boundary layer. We also briefly transformed the compressible laminar boundary layer equations with the intention of finding some self-similar forms. Transformed 2D laminar compressible boundary layers equations, the energy equation, skin friction and heat transfer coefficient, simplification of transformed compressible laminar boundary layer equations for flat plate, all these were covered in this week. And then finally, after having derived the self similar form of those equations, we looked at velocity and temperature distribution within laminar compressible boundary layer for flat plate, both for adiabatic and isothermal walls. And then we discussed about the implication, that is aerodynamic heating due to viscous effects, and we also looked at stagnation point flow. With that, we moved on to week number 5, where we begin by calculation of compressible laminar boundary layer on a flat plate at hypersonic Mach number, both a sea level as well as 15-kilometer altitude conditions, and we tried to compare the outcomes. We looked at drag, the heat flux, skin friction coefficient, Stanton number, some of the things which are of practical relevance, and then the basic thermodynamics was again recapitulated both for real gas and perfect gas. We looked at the equation of state, and then we started discussing about the equation of state for a pure gas as well as gas mixture. Whenever it comes to the gas mixture, of course, we introduce the partial pressure and Dalton's law. Not only that, we also looked at the equation of state under different bases like mass basis, mole basis, particle basis, which was subsequently used time and again in the remaining weeks of the course numerous times. Important relations between species parameters and mixture parameters, entropy of a gas mixture, concept of irreversibility due to thermodynamic non-equilibrium, all these very important concepts were introduced. Therefore, we were gradually getting into chemical non-equilibrium, and that was of paramount interest in the context of hypersonic flows, where quite often such non-equilibrium situations can arise. Gibbs free energy of a gas mixture, condition for chemical equilibrium, the introduction of equilibrium constants, introduction to behavior of high temperature air at 1 atmosphere pressure, the excitation of different modes like vibrational excitation, dissociation, ionization, all these very important concepts were introduced. Equilibrium chemically reacting gas mixtures, composition, how we calculate it, such things were discussed at this point, and we also introduced the concept of heat of reaction. With that, we wrapped up week 5 and moved on to week 6, where we started by discussing about excitation of various molecular energy modes in a single species gas, where you consider gas to be, say, an atomic medium or comprising of molecules, and therefore, what are the different energy modes which can exist: translational, rotational, vibrational, electronic energy modes. Then the quantization of the energy levels, energy level diagram, 0 point energy, number of states, degeneracy or statistical weight, microstate. So, we were essentially talking about statistical mechanics and microscopic thermodynamics in this portion. We further moved on, we looked at concept of thermodynamic equilibrium in statistical thermodynamics, the most probable macro state, counting the microstates for a given macrostate, and then we looked at the Bose-Einstein and Fermi-Dirac statistics, and then we saw that under some condition they do converge to the Boltzmann distribution, which is most often used for describing equilibrium. Then the concept of partition function was introduced at this point, and thermodynamic variables were expressed in terms of partition function, which we did for internal energy and enthalpy. Connection between entropy and maximum number of microstates was discussed, and that was explained as the connecting link between classical and statistical thermodynamics. Boltzmann constant, entropy and pressure in terms of partition function, energy mode expressions from quantum mechanics, expressions for sensible energy for atoms and molecules, temperature dependence of thermodynamic properties of single species. Many such very important concepts, some of them which may be new to you, were introduced here. Variation of CV as a function of temperature and pressure for a single chemical species, and chemical reactions in high temperature air, the independent chemical reaction equations, how we choose them, the mass balance equation, the electric charge conservation in ionized air, equilibrium composition of high temperature air, mole fraction of different species in high temperature air at 1 atmospheric pressure. Such very interesting, perhaps new concepts for many of you were introduced in this week. Then we moved on to week 7, where we discussed about recapitulation of equilibrium chemically reacting flow composition, which we had done in the previous week, but we again revisited it, and then we discussed some of the concepts which we earlier covered for convenience. Then significance of kinetic theory of gases in the context of hypersonic flow, gas particle motion, particle velocity, collisions, specular reflection, translational energy, particle cross-sectional particle collision cross-section, mean free path, particle collision frequency, different measures of velocity like mean square velocity, RMS, sphere of influence, number density. Some very important concepts from the kinetic theory point of view were introduced in this week. And then we accounted for relative velocity between colliding gas particles, and then the equilibrium velocity distribution, which gives the Maxwellian distribution, and speed distribution functions were discussed. And then we moved on to vibrational non-equilibrium and vibrational rate equation derivation, where we talked about the master equation, concept of vibration relaxation, the concept of detailed balancing, and consequently the rate equation, where the vibrational relaxation time was an important feature. And then we moved on to chemical non-equilibrium, where we derived the chemical rate equation. So, we accounted for forward and backward reactions and the corresponding rates, from where we derived the net reaction rate and the law of mass action, which was generalized. We looked at Arrhenius equation, dissociation and recombination reactions, chemical rate equation for high temperature air. Again, in this week, a lot of new things were learned. Then we moved on to equilibrium requirements of high temperature gas mixture, thermodynamic and chemical equilibrium, thermodynamic properties of a high temperature equilibrium chemically reacting gas mixture, heat of reaction and heat of formation and their significance in calculating thermodynamic properties of an equilibrium gas mixture. We also learnt about the Mollier chart. Once again, you might have learnt it in your earlier thermodynamics and courses related to power plants, and then some polynomial correlations which may be useful, and then the conservation equations for inviscid high temperature equilibrium flow were learnt. We also learnt about some iterative schemes to solve for flow properties for in inviscid chemically reacting equilibrium flow through a shock. Inviscid high temperature equilibrium flow through normal oblique shocks were discussed. Shock detachment distance in front of a bluff body, equations for calorically perfect quasi one-dimensional flow through a CD nozzle, approach for calculating equilibrium flow through a CD nozzle, all these were discussed. Comparing calorically perfect and equilibrium flow was done, and with that we also discussed briefly about equilibrium flow, frozen flow, flow time, reaction time, and these concepts were further elaborated later. In week 9, we discussed under what circumstances do we envisage non-equilibrium flows occur. We discussed again about vibrational rate equation and relaxation time. We introduced the two temperature model of Park, which finds wide application in hypersonic flow computations. Conservation equations for inviscid high temperature non-equilibrium flow were discussed. Incorporation of chemical rate equations and vibrational rate equations was done. The species continuity equation was introduced along with the standard conservation equations. We discussed about the concept of frozen equilibrium and non-equilibrium flow in terms of the important relevant time scales, namely the fluid dynamic time scale and the chemical reaction time scale. We discussed about non-equilibrium, normal and oblique shock flow. How does the flow behave across such discontinuities when non-equilibrium persists? And then we had a discussion about non-equilibrium CD nozzle flow as well as blunt body flow. We briefly introduced the concept of binary scaling. With that, we moved to week 10, where we revisited viscous effects, dissipation, aerodynamic heating, and kinetic theory with its connection related to viscous transport phenomena like momentum, heat and mass transfer. These were introduced. General transport equation for a property using simplified kinetic theory approach was introduced, which helped in modeling viscous transport phenomena like momentum, heat and mass transfer. Transport coefficient expressions for pure gas and gas mixture was discussed. Flow velocity versus diffusion velocity were discussed, and then high temperature transport properties were of air were introduced. We then looked at relation between flow velocity and diffusion velocity due to species concentration gradients, and modification of the species transport equation to account for the effect of diffusion velocity. Governing equations for chemically reacting viscous flow were visited. Different forms of the energy equation were introduced. Boundary layer equations for chemically reacting viscous flow were introduced. Earlier in the course, we had discussed it without chemical reactions. Here, chemical reaction effects were introduced. Relevant similarity parameters were identified, and we found that they were Reynolds number, Prandtl number, Lewis number and Eckert number, which figured newly for reacting flows. Introduction to radiative heat transfer, which could be of paramount importance in hypersonic flows, was done, and that relevance in blunt body stagnation region was discussed. Some computational results were also shown over here for chemically reacting flow solution around a blunt body. We also very briefly introduced astrophysical flows here. Moving to week 11, supersonic and hypersonic flows through nozzles, different problems associated with continuous flow hypersonic wind tunnel, including problems of storage of high pressure, high temperature gas was discussed, and then we discussed about high enthalpy, high temperature facilities, including shock tubes and shock tunnel and their applications, CD nozzle flow, wave reflection from free boundary, shock wave incident on constant pressure boundary, or expansion wave incident on constant pressure boundary. These were discussed along with diamond wave pattern which may form downstream of a CD nozzle. We learned about pressure deflection diagram, and then we started introducing the shock-shock interaction problems. We learned about type 1 to type 6 shock-shock interaction according to the Edney classification. We learnt about the very important phenomena of shockwave boundary layer interaction, then briefly about lifting entry, ballistic entry, atmospheric entry of vehicles of different configurations, their flight path, and all this way what we have been seeing, you can also revisit them later, because these are essentially the concepts covered which have been documented as a part of the course contents, and these are essentially the keywords that we have been providing you from time to time. The hypersonic flight trajectories, basics of wave rider design and the reason for its supersonic aerodynamic performance. The reference temperature method, which is a very important engineering significant method, was introduced and its relevance was discussed. Finally, week 12, where we again discussed about reference temperature method by applying it to some problems and demonstrating its capability. Then we briefly discussed about boundary layer transition, and we started recapitulating the Navier-Stokes Fourier equations, but this time we introduced it in flux vector form, and we discussed it from the point of view of its application in an open source CFD solver, namely the Hy2Foam, where we discussed at length about gas mixture properties, partial pressure, transport property like molecular viscosity, thermal conductivity, mixing rules where a lot of species are existing in the gas mixture, mass diffusion, application of the two temperature approach of Park, etc. From the numerical implementation point of view in an open source CFD solver was discussed, and then we showed some results from our in-house simulations related to shock diffraction across a triangular wedge corner and a right angle step corner, hypersonic flow over a hollow flare and over a double ramp, and we saw very interesting results here. We saw, for example, in the shock diffraction problem, the lambda shock, primary vortex, shear layer, cage instability, acoustic waves, vortex induced shock, flow over a flare, a little bit of shockwave boundary layer interaction on the base of the step or the triangle, and then in the flare problem, the excitation of translational temperature, vibrational temperature, and then towards the end we saw a little bit of the double ramp problem, which is very important from the point of view of the inlets or intakes, which we discussed in a later lecture in week 12. High speed intakes and combustion issues in scramjet engine, some other applications of shock waves like medical, detonation waves, volcanic eruption was taken up in the subsequent lecture, that was lecture 59, in connection with intakes, scramjet engine processes, lithotripsy, shocks in detonations, shocks in volcanoes, and finally the lecture 60, which we are currently going through and almost coming to the end of the course, where we have seen a little bit about astrophysical flows being simulated through an under expanded jet at high Mach number, which represents like a stellar wind problem, and accretion disk, which is kind of a representative of a black hole kind of a problem. All these things were covered in the course, and I hope it has been useful. So we try to conclude here saying that in this lecture we discussed about one other application of shock waves, that is astrophysical flows. We completed the course by recapitulating the main topics covered in this NPTEL course in brief, and thank you for your very active participation. I hope you enjoyed the course and you benefited from it, and I thank all the supporting staff at the NPTEL offices spread at IIT Kanpur, IIT Madras, and other institutes who are stakeholders, who are helping us all the way through. They are working round the clock behind the scene, and they have been recording them, editing them, putting them up from time to time in the web, so that you can access the material seamlessly all through the course. So I hope you have enjoyed their participation, you have enjoyed my course content, you have found relevant material in the course. I also thank my TAs who have very effectively supported me all through. So thank you, and we'll end the course here. Thank you.